Okay, a couple of lift examples. So this is connected objects in contact, but they tend to be lift questions. So we've got a man of mass 90 kilos is standing in a lift of mass 300 kilos, which is accelerating upwards at 0.6 meters per second squared. Find the tension in the cable and the reaction between the man and the floor of the lift. So in terms of working this through, we can treat the system as a whole. So we've got the lift, we've got the cable's pulling up on the lift, so we've got tension, and we've got the man in the lift, and he has a mass of 90 kilograms, so we've got 90G acting down, and also the lift has a mass of 300 kilograms. So the total weight acting down will be 390G. What's happening when you treat the system as a whole is there's these reaction forces. So when you went up and down in the lift on the scales, there's the reaction force that acts up on the man, and there's the reaction force that acts from the man down into the lift. But because they're equal and opposite, they cancel each other out. So we can treat this as a whole to find the tension in the lift cable. So it's accelerating upwards at 0.6 meters per second squared. So that's going to be my positive direction because it's moving upwards. So we've got T minus 390G, that's the weight acting down, is equal to the mass times by the acceleration. And when you work that through, T comes out as being 4056 newtons. And then to find the reaction between the man and the floor, we need to think about what forces are acting just on that person in the lift. So just homing in. So this is, we looked at this before, but all that the man is experiencing is his weight acting down, which is 90G, and the reaction of the lift between him and the floor of the lift acting upwards. So setting up an equation of motion just for the man by himself, again positive direction is upwards, then the reaction force minus 90G is equal to the mass times the acceleration, and that gives you the reaction force as being 936 newtons. So you don't have to write it in when you're treating the system as a whole, but there's the reaction force upwards from the floor of the lift on the man, and there's the reaction force downwards that's acting from the man on the lift. But when you're treating the system as a whole, they cancel each other out, so you can ignore the reaction forces. I will also go through the example which is from page 463 in your textbook. So this time we have a woman. Sorry, just find my notes a minute. Of mass 60 kilograms standing in a lift. Draw a diagram showing the forces acting on the woman. So very similar to what we've just done. So we've got her weight acting down and the reaction force. It's a bit hard to draw it in with a person as well, but we've got this reaction force acting upwards. And Find the normal reaction of the floor of the lift on the women in the following cases. So the first one is the lift is moving upwards at constant speed. So if you're travelling at constant speed, then the forces are in equilibrium. So the reaction force would equal 60G. And 60 times 9.8 gives you 588 newtons. And then the next scenario, the lift is moving upwards with an acceleration of 2 meters per second squared. So I would now take my positive direction as up, but the same forces are acting. So R minus 60G is equal to 60 times 2. And that gives you the reaction force as being 708 newtons. So when you went up and down in the lift, when it was accelerating up from the bottom of the building, you got that stronger reaction force. So this is just quantifying it all a little bit more. And then part 4, the lift is moving downwards with an acceleration of 2 meters per second squared. So I would suggest you just swap everything around. So it's accelerating down. So if you take the positive directions down, then we've now got 60G minus R is equal to mass times acceleration. And that gives you a reaction force of 468 newtons. So you get less reaction force accelerating downwards. And then part 5, the lift is moving downwards and slowing down with the deceleration. So because it's moving downwards, I would keep positives down, but because it's slowing down, the acceleration would be minus 2. So we end up with the equation of motion as being 60G minus R is equal to 60 times negative 2, and then R comes out as being 708 newtons, as it was up here. So I'm hoping that makes sense, okay? And then the last bit, in order to calculate the maximum number of occupants that can safely be carried, the following assumptions are made. The lift has mass 300 kilograms. All resistances to motion may be neglected. The mass of each occupant is 75 kilograms and the tension should not exceed 12,000. So if we set this tension at 12,000, and then we've got people in the lift. So, sorry, my people aren't that eloquent, but they'll do. So we've got N people in the lift. And so acting down, we've got the weight of the lift, which is 300 kilograms. And then we've got 75 times N kilograms times 9.8. So that's the weight, total weight acting down. And then like we saw before, there's all these reaction forces. So there's the reaction force acting up on each person, and each person is creating a reaction force acting down into the lift, but they're cancelling each other out because they're equal and opposite. So we can treat the system as a whole, ignore the reaction forces, and we end up with 12,000. So what's the greatest number of occupants carry safely if the magnitude of the acceleration does not exceed 3 meters per second? So we're going to take it accelerating upwards at 3 meters per second squared, sorry. So that's the positive direction, and that causes maximum, that'll cause you maximum tension accelerating upwards. So 12,000 minus 300G minus 75 ng is equal to the total mass times the acceleration. It looks a bit complicated, but remember G is just 9.8, and once you plug in G, it actually comes out quite nicely. So we end up with 9060 minus 735n equals 900 plus 225n, just expanding brackets and tidying up. So here I'm subtracting all of this. And then n comes out as being 8.5. We want the maximum number of people that can be safely carried, so we don't really want to round that up. So always think about which way to round in these sort of questions. So maximum number of people will be 8 occupants. So you can treat the system as a whole, or you can come in and just look at what's happening within the lift itself. So I'm hoping that makes sense. From there, there's a sheet I gave you last lesson, so if you weren't sure about that, have another look over that. And then also in your textbooks, there's page 466, question 4, which has some letters in, but don't let that put you off, and question 9, so just in case you wanted a little bit more practice on those.